everyone. Here I'm gonna talk about my project for course ECE 598. The title of the project is Predicting the Spectral Energy Density of Multilayer Structures Using Deep Neural Networks. Here we have the structure under study. The structure has 6 layers. A layer which is M6, the layer with thickness of 1 millimeter, is using as the substrate to fabricate the other layers that has much smaller thicknesses on top of that. And what we want to measure? We want to measure energy density, which is generated by electromagnetic waves. I'm gonna simply talk about this about energy density. The electromagnetic waves, each everything that has temperature higher than 0 Kelvin and generate electromagnetic waves. And the electromagnetic waves contains energy. The energy is storing in electric field and magnetic field. We want to measure that energy in at this point, which is 100 nanometer far from the top layer. At this point, we want to measure the energy density. Here we have the 10 available materials that are using in these 6 layers. What are the features? What are the input features? First, I should mention that the project is designing a linear regression model. We want to give the model the features, the structural features, and the model predict for us the spectral energy density that we will see a training sample in the next slide, and we will explain that. The input features are, we have 11 input features. 5 of them are continuous features, the thicknesses of the layers, T1 to T5. And T1 to T5, the thicknesses can vary from 10 to 500 nanometer. And they are randomly selected. And we have six categorical features here, which are the type of the materials that are picked from these 10 available materials. When you want to pick the materials, we consider this. We decided to pick the materials that are stable at high temperatures and are good for fabrication. What was the reason? Because after designing this model and then design the inverse model, I will talk about the inverse model. We want to use the neural network model to predict the structural features of the desired, spectral, the desired energy density spectrum, and then fabricate that structure and test it in the laboratory. So first we need to consider the materials that are stable at high temperature. The temperature is about 600 to 700 Celsius. And here I should mention that we have a categorical, when we consider the categorical features, the convergence of the model, this linear regression model, will be harder. Most of the papers, most of the researchers that have been done consider just continuous features, like the thicknesses of the layers, the gap size between the plates, or this distance that we want to measure the energy density at. These continuous features that are much that if we just consider these continuous features, the convergence of the model will be much easier. And here we we encoded these materials, these 10 materials, with numbers from 1 to 10. There are several ways to encode these categorical features, like one-hot encoding, target encoding, and so on. But we couldn't use them. Why? Because in the inverse model, that I will talk about it later, we have a part which is classification, and we needed to index the materials with these numbers from 1 to 10 and use them as the classes that corresponded to each of these materials. Definitely using the encodings, the other encodings, like for example target encoding especially, could improve the performance of the model, but we couldn't use that. Here we have one training sample. Here we can see that we have 11 features. 6 of them are the numbers corresponding to the materials, and we can see that the repetition is loud. We can use the one material in more than one layer. We have these categorical features and the thicknesses, the continuous features. Yeah, we have totally 11 features, and this is the corresponded output, because this spectral energy density to this input. And what is the output of the model? You have this spectral in this range, in this frequency range. We discretize that into 200 points, and this is the output of the model. So the input, each training sample has 11 features as the input, and the 200 points, 200 spectral points as the output. For training the model, I generated 1 million dataset for training samples for training, and 200k for validation, and 100k for as a test dataset. We used this is the sample before normalization, because when I wanted to before training the model, I used minimum and maximum in each column to change the range of the features and also the output to 0 to 1. This make the convergence easier and improve the performance of the model, definitely. Here we have the schematic of the model. The forward model. Why I name it forward model? Because this model learned how to map the structural features to the output spectral. So this is the forward model. The inverse model will be if we give the model the spectral, the output, the spectral, and expect the model to predict the structural features, structural properties for us. This would be the inverse model. The forward model is mainly created from dense layers, the fully connected layers, and we have hidden layers, and we tested different number of layers and number of neurons. We'll explain it in the next slide. Here we have different models. Here we have the layers from 1 to 5, the number of hidden layers, and different batch sizes. For training the model, we used Adam optimizer. Why Adam? Why not stochastic gradient descent? We tested a stochastic gradient descent, and it was very low compared to very slow compared to Adam Optimizer, and it needed I limited the number of epochs to 1000 epochs, and if I wanted to use SGD, we needed much more epochs for convergence. And I used the default hyperparameters of Adam for all the models, with the exception of this model, which has the best performance here. The batch size is 512. This is the same. These two models are the same. The batch size is 512, but I increase hyperparameter epsilon, which is kind of like the learning rate, that epsilon. When I increase it, uh, the updates that are making the weights of the model become smaller. And then I saw that the performance of the model improved. Here we have the best model. And regarding the loss function, I used mean absolute error. Why I tested mean square error, and I saw that the performance of the model with training with mean absolute error was much better. And here we can see the training and validation loss. We can see that for plotting this, I skip 250 first epochs because of the fluctuations to see the convergence much better. Here it's common that the the validation loss be a little bit slightly higher than the training loss, but this is not a trend here. We cannot see that here. Maybe one reason could be that the validation, but at first, uh, the validation loss was higher than training loss. But here, the reason could be the validation loss is measured when the epoch is done, when the training is done. But the training loss is measured during training. One reason could be that. And I need to here after that we talk about one problem. But before that, I want to present the predictions of the model. Here we have 4 random samples from the test data set. They are randomly selected, and we can see that the model predicts the trends properly and is accepted. For us, it's very important that the model be able to predict the peaks, these regions. Very good, and this is the case here, because these regions, when you want to measure the total energy, we need to get the integration of this area under the spectrum. And if we have error in these parts, the total error will be higher compared to these regions which are not peak. Here we can see the predictions that are accepted, but definitely the model can be improved. And in the next slide that I'm going to talk about the future works, I will talk about some improvement that can be done in this forward model. And here during training, I had a problem, and the problem was that the model, which is common in regression problems, the model predicted some negative values while all the training samples or the output of the training samples were positive. And how I solved this problem? By changing the activation function of the last layer. I tried different activation functions. Like one of them was soft plus, which is in cross and could use it. And I should mention that I implemented the model in cross, and I use that soft plus and also some other using exponential and logarithmic functions as the last activation function, the activation function of the last layer. But I saw that the getting the absolute value of the output of the last layer was the best. So the problem was solved, and the model, we can see that do not uh, predict the negative values here. Talking about the future works. The future works will be uh, designing the inverse model. What is the inverse model? The inverse model will be, for the forward model, we give the structural features to the model and expect the model to predict the spectral for us, the output for us. The inverse will be giving this spectral to the model, and once the model to predict the structural features for us. This is the inverse. Why we cannot just give, because the model doesn't have understanding about the physics under the, you know, the physics of these values that we give the model as the training samples, doesn't have any understanding about it, just see them as numbers. Why we cannot discretize this and give it to model as the input, and this 11, for example, 11 features in our case, this is not our case, just as an example, and give it to the model and consider it as the output, and just swap the, you know, the input and output. Here we cannot do that, and the model won't converge. Why? Because, for example, here we don't consider the categorical feature, just the thicknesses of the layer. Expect that this red ones has the same, material, and the blue ones, just, alternating, the type of the materials. Here we have different, two different structures with different thicknesses of these layers, but both of them produce, the same spectra. So if we consider this as the input, for one input we have two output. So this is, this make the convergence impossible. But for the forward case, each structure have, one just one output, a spectral output. So the convergence is possible. But here, this is a problem. But how can we solve it? Here, we have now this model. The forward model is pre-trained. Okay, this is considered as a machine. When we give this 11 features, the model can predict these 200 points for us. Okay, now we can freeze this. Okay, freeze the weights of this model and connect it to this part. This is the inverse model. Okay, and train the model. Train these weights here. The hidden layers could be again selected with trial and error. And train this model and use backpropagation to update these weights as they. We have three loss functions here. What are them? One of them is that this predicted, really predicted by this whole model, this 200 points. This predicted ones, 200 points, the distance between these points and these ground truths, the input ones. One of them is that, again, we can measure that with MSE or MAE, mean absolute error, or mean square error. And the other loss function will be here. We have the classification. I talked about it earlier. Here we have classification. They are categorical features. Okay. This input, this input has the correspondent 11 features. Okay. For the 6 categorical features, we can compare them with these 6 ones and use cross entropy. And this is the second loss function. And here for these 5, again use linear regression and use MSE or MAE. Another loss function. So we have 3 loss functions, and the total loss function will be the weighted average of these 3 loss functions, and we train the model to update these weights as it can produce predict the features that are correspondent to these 200 points, and this will be the inverse model. So and then after that we will use this inverse model to predict, because we have a desired spectral, these 200 points we have a desired one. We want to predict the structure, predict these 6 categorical features, this material, type of materials, and these 5 thicknesses, and then have our optimum structure and then fabricate it to test it in the laboratory. This is the goal of this project. Here as the project for this course I finished the first part. For the next part I need to design the inverse model and then use it for the next step, doing the experimental test. Thank you so much for your attention. It would be a great pleasure for me to answer your questions in the comment. Thank you and